Okay, thank you once again for joining us on this Saturday. We're going to be talking about solar PV design and sizing, and we really don't have much time because we have a lot to discuss today. So I think I'll just skip this protocol and jump into the solar PV design sizing. We're going to deal with the calculations today, so it might be helpful to have your calculator handy. If not, I know most of us have already gotten rid of our calculators, especially maybe the scientific calculator, but it's fine. You can make use of your phone. We are not doing any scientific calculations, just basic calculations. So your phone can serve in this purpose. So sizing a photovoltaic system or PV system. For a standalone photovoltaic power system involve 5-step process that will allow the photovoltaic system designer or user to accurately size a system based on user's projected need, goal, and budget. Now, these steps are estimating the electric load, sizing and specifying the inverter, sizing and specifying batteries, sizing and specifying an array. Of course, you know that modules, when you put modules together, it forms an array. And of course, the final stage is specifying a controller. You have to size and specify the controller as well. So we're going to go through all of these stages, and we'll see we're going to walk through the calculations. So first of all, the purpose of having a PV system is to serve a certain purpose, and that purpose is to meet demand, electrical demand. So you usually need to start from the demand. You don't start from the supply. Now, PV systems are supply side, right? They supply electricity to the demand. So you need to start from the demand. What exactly do you want to size? So you need to conduct a simple energy audit. This is not going to be a detailed energy audit like we are trying to identify. Now, it depends on the objective, though. If the objective is holistic, what do I mean? If, for example, you're trying to provide a sustainability roadmap, okay, or you're trying to develop a energy transition plan for an organization. So it depends, but in this case, we're looking at the basic situation here. We're looking at the basic design system here, okay? So you just need basic load that you need to power. But it also makes sense to look at those load that you want to power and see if there are energy efficiency recommendations you can make first. So for example, you might look at their TV system, their refrigerator system. If budget allows, depending on the financial capability of your clients, if budget allows, you can as well recommend for more efficient refrigerators or standing fan. If there are DC fans that you can recommend, which are less energy demanding, you can recommend all of those. So this is where you have to put on your energy efficiency thinking cap, right? But in this case, it's not as intense as an industrial energy audit like we did in our first batch of the training. But it's also very important that you understand the load, look at the TV systems and see what energy efficient upgrade you can recommend. If they intend to power an air conditioning system, in which case it might be recommended to go for an inverter type air conditioning system if budget allows, because I know those kind of appliances are a little bit more expensive than the conventional appliances. However, over time, it's going to be cheaper because they're going to save a lot of money, by using those appliances over time, and then make up the gap in the cost of purchasing the equipment. So this is our typical example of what we want to power with our PV system. Okay, so we have 4 items here. We have just basic items: television, fridge, light bulb, standing fan, and we have the quantity. You have for television, this client has just 2 televisions. He has 1 refrigerator. He has 8 light bulbs and one standing fan. And these are the ratings, the electrical ratings of these appliances. And in the power demand, okay, you have 2 televisions. If you times that by 50 watts, assuming that the television is 50 watts, if you times by 2, you have 100 watts. And then the hours of usage in a day, you also need to understand how often this client is going to be using these appliances on a daily basis, okay? So the television is assumed that it's going to run this television for just 6 hours, sorry. And then for the refrigerators, it's going to run for 12 hours, light bulb 8 hours, standing fan just 1 hour. So we have this basic variable, very basic input. You can then calculate their energy requirement. Energy requirement is power times time. You know the power already, which is 100 for television. That's for the two combined, and the usage is 6 hours. If you do that multiplication, you have 600 watt-hour per day. Now, this is the energy requirement per day. Okay, so you do that across these 4 items, and we have the total values here. The power demand for this client is 410 watts, and the energy for daily energy need is 3,400 watts hour. Okay.
Chima. Hello,
yes.
Chima.
Yes, please.
Yeah, good morning, everyone.
Yeah, good morning, Mike.
I think we'll be looking at realistic values here now. Like, if you're liking this to somebody with a room and parlor,
okay,
then we can look at the television timing for 6 hours. Yeah, but the one of the fan,
okay,
does not look realistic because there's no air condition working. You cannot depend on natural drought. So look, if something like 12 hours is or 8 hours, it become more realistic. That's a workable
okay.
data.
Okay,
not 1 hour.
Okay.
I even feel that the fridge. I don't know how many.
Yeah, the fridge 12 hours is okay.
Okay.
You put it off during the day, or during the night, depending on the one that you choose.
Yeah. So as energy efficiency measures, sometimes if your fridge now, it also have to look at. So sometimes when I try to recommend people trying to turn off their fridge at some point when it or not just turning off entirely. Sometimes there are thermostat control for the refrigerators. Not a lot of people do that anyway. So you have to tune your thermostats to your demand. Okay. Sometimes a lot of time we turn it to the lowest temperature, and then when you pull out any item from your fridge, it's as strong as a rock. Right, and what we do again, we have to just put it inside the microwave and start heating it. So sometimes it depends. What your food storage temperature is also very important. You don't need to make it as strong as as a rock before you can preserve it. But I can understand that because of the situation in Nigeria, you can't predict when there's going to be power supply. So you might have 2 days running without power supply. So if it's as strong as a rock, then for that 2 days it can retain its temperature and not get bad, right? But for places where you have a good level of power supply, you don't necessarily need to tune it to that very low the minimum temperature to operate. So your fridge works with a thermostat. If it gets to a certain temperature, it goes off. Then after a while, it comes on again. That's the way these cooling equipment are designed to work.
Okay.
But a lot of time we don't understand. So even if you have a refrigerator that is on for 24 hours and you tune it very well, the thermostat, it does not mean that it's running actively for 24 hours. So it can switch on and off just like your air conditioning system, right?
Okay.
Yeah. So now for the purpose of this training, your inputs are valid and have noted them in terms of maybe the standing fan, the hours of use of the standing fan. Yes. Okay, let's just see this as this is an example, but we can adjust this and then rework this. But let's work with what we have currently, because if we need to start doing if I make changes to this, I will need to make change to every calculation that has done.
Let's just go ahead.
Exactly.
Clarity.
Yeah, sure. I totally agree and understand with you. So let's move on. So let's understand that the demand here is 410 watts, right? And the energy demand per day is 3.4 kilowatt or 3,400 watt hour per day. Okay. So let us start with the very first one, which is the sizing of the inverter. How do we size an inverter? So we size inverter based on power demand, not energy demand. Inverters are sized based on power demand, and our power demand in this case is 410 watts.
If I may, the 410, is it instantaneous or what? Please, sorry.
So please, power is instantaneous, always. Always, anytime you see, and in our first training, I try to distinguish this. Power and energy are different things. Power is always instantaneous. Is a universal principle anywhere. Anytime you see power, it's instantaneous. It's not depend on time. When you add time elements, it becomes energy. That's the difference between power and energy. Okay.
Thank you.
Energy that has time comes. So power times time become energy. And that's why we have energy requirement in this last column. Okay, so we're selling inverters based on demand. Okay, and our demand in this case is 410 watts. If you divide that by 1,000, it becomes 0.41 kilowatts. Okay, so here's the way we do this. Okay, so you have to make some certain assumption of your desired load factor. Sorry, just give me 1 minute. Let me take care of something. Okay, sorry for that brief interruption. Yeah, so can you hear me? Can you hear me?
Yes, we
can hear you.
Okay,
yes.
okay. Okay, sorry, yeah. So we assume a desired power factor of 70%. Now, 70% power factor is like, okay, the energy demand is, the power demand, sorry, is 410. But you're not just going to give them or size their inverter to be 410 watts. When you go to the market, inverter can be sized in watts or in kVA or VA. So we have to pay attention to the units, okay? Sometimes you see some inverter, they will tell you it is maybe, for example, 2.5 watts. I'm beginning to see some of those kind of ratings in the market. But ideally, inverters are rated in kVA. Ideally, they're rated in kVA or VA. So pay attention to the unit, okay? So in this case, our demand is 410, but we want to assume a load factor. Now, a load factor is a safety margin, okay? I will rather make an advice here that the maximum you can do or you should do is about 70%, and this allows for fluctuations and inrush current. And you know, sometimes when you're starting some appliances, they have this inrush current. They draw more excess current for a start, especially for inductive load. They draw in more current. So when you have those kind of, or even spikes, we have those things. It creates tolerance for the
like your water pumps.
Yes, so you create tolerance for your inverter to withstand some of those, spikes and excess, demand. Okay, so I think 70% should be the ceiling that you should go, okay, to allow for that. You can even do 50%. If you envisage that your client is going to add more load, you can even bring it down to a little bit about 40. If you envisage, or if your client say, okay, in the next few months, I'm going to add additional load, meaning that this 410 will also increase. So you can create those kinds. So you need that conversation with your clients to understand their demand and then design to meet that demand. Okay, their near and future demand as well is very important. So what happens is here is that you have to divide that your peak demand, which is 410. 410 in this case is our peak demand, right? We have to divide it by the load factor, which is 70%, that's 0.7. Then we have a value of 585.7 watts. Okay, now this is in watts. This is the size of our inverter in watts. Okay, and with the mind of 70% load factor, you can do 50% load factor, it's fine. Okay, but for this purpose of this assessment, we're going to use 70% load factor. Then we have 585.7 watts. Now, if you go to the market, you will likely see most inverters rated in kVA or VA. So you need to convert this watts to kVA as well to know what the value will be in kVA. Now, to do this, you will need a power factor value to be able to do this, to convert to kVA. Sorry, is my screen moving? I'm reading something that my screen sharing is paused. Is it moving? Oh,
when you say
Not moving,
but we're following
we're still in the page that you are describing.
Okay. let me, because I'm kind of, I'm seeing, let me stop sharing and then share again. I'm reading a question now. Your screen sharing is paused. I don't know what I have pressed. Okay, so we are back to the current page, right? Correct?
Yeah.
Yes.
Okay, okay, thank you. Yeah. So now to convert the power into the apparent power, which is kVA or VA, we need a power factor element. So in this case, we assume a power factor of 80% or 0.8. So what we're going to do is to further divide this active power by 0.8. So when we do that division, we have 732.125 VA. Now, always pay attention when you do your calculation. Be careful of the unit. Now, this is VA, not kVA, but VA. If you want to get this in kVA, which you also find some inverters rating, you have to also divide this again by 1,000. So this will be 0.7, right? Remember, we started with, if this were to be, okay, this is this active power. So now, for this demand, your inverter size, with this assumption that we've made so far, load factor of 70% and power factor of 80%, your inverter size should be 732.125 VA. So we have succeeded in sizing our inverter based on these assumptions. Okay, so we are going to move to the next one, but before that time, I just want us to just do a little exercise. So this is exercise I want us to do. So do this calculation, this same load characteristic that we've had, do the calculation with a required, now if the required peak size, now we have 410, right? But in this case, do your own calculation with 750 watts. So let's assume that in this case now we've added more appliances, we added more, maybe refrigerator, more appliances, and now it has now gone up to 750, and we want to maintain a power factor of 0.85, that is 85%. In this case, our load factor is going to be 60%, not 70%. So I just want you to run a calculation, size the inverter based on this new characteristics or variable that I've presented to you. Please, let's quickly do this. This shouldn't take more than, in fact, 1 minute is okay for this, please.
What was your load factor and what was your power factor, please? Can you?
It's given the question. Load factor is 60%, power factor is 85%. If you can't read the question, let me know. If you can't see the question, let me know.
Okay, on the exercise. Oh, I see. Okay.
Yes,
okay.
yes.
Thank you.
$1,470.588 volt amps VA.
Okay. Any other?
So for the inverter size, I think you'll be looking at 1,250 watts.
Okay.
And then for the oh no. So that, okay, yeah, that was the initial, that's based on the load factor. Okay, I've not applied the power factor, so we have to apply the power factor now. So that gives us 1,470 VA.
1.47 kilowatts.
Yeah.
Okay, yeah, 1.47
kVA.
Not kilowatts, please.
kVA.
kVA, correct. So if you're using kilowatt, please kVA divide by 1,000. So you have 1.47. Yes. If it's VA, then 1,470. Let's just be clear on that. Okay. So yeah, I think we're absolutely correct. I mean, we're all following this calculation. So let's move to the next one. Sizing of battery. Now, remember when I talked about sizing of inverter, I told you that sizing of inverter is depend on the demand, on the load. Now, battery is different. Battery is on the energy. Sizing of a battery is on the energy, not on the demand, right? So in this case, our energy demand is 300. Now, when I say energy demand, please let's not get confused, because sometimes it can look confusing. Power demand, energy demand. If it's power, it is instantaneous. If it's energy, it is over time. Correct. So now we're talking about battery. What is going to be the daily battery demand, which is 3,400 watt hour. Okay, that's their daily energy demand. But when you're doing your design, you don't assume that the sun will always be out there every day of the year, 365 days in a day. You don't make that assumption. You also assume that there could be days when the sun is not going to come out. It can run all through the day. That does not mean that the solar will not produce. It will produce at minimal level, correct? But again, we assume that, okay, it's not going to produce anything significant to serve the load for that day. So we usually do what we call days of autonomy. If you hear such terms like days of autonomy, what that means is that the days when there will be no sun, okay, maybe a cloudy day or rainy days where there is minimal production on the solar system, and again the client needs energy to work. In this case, you need to plan for that in your design. So in some cases, it might just be 1 day of autonomy. What that means is that if for 1 day there is no sun, your client is still okay. There is enough energy storage in the battery to last for that 1 day. But if it lasts for 2 days, then there's going to be a shutdown, or it has to look for another alternative supply. In some cases, you could have 2 days autonomy. But let's bear in mind that the higher the number of days of autonomy, the higher your battery capacity and the higher your capex, your investment for those systems. So you need to also find out, what budget available and the cost of the technology you also want to apply, because we know that battery is very expensive. Even up to today, the prices are coming down, but it's still expensive. So in this our own case, let us assume 2 days of autonomy. So we have one day demand, which is 3,400 watt hour, but we want to add 2 days of autonomy. Should in case if there is no sun for the next 2 days, we want this load to keep on. We want to keep this load on for the next 2 days. Okay. So we have 2 days of autonomy, and if what happens here is that we add these 2 days of autonomy to our daily demand, okay, which will now take our demand from 3,400 to 10,200 watt hour. So we are sizing our battery bank for 3 days. That's what this means. Now, this 10,200 watt hour is the usable size. That is what is obtainable from the battery, what you can deliver to the load. Okay. Now for batteries, there's what we call depth of discharge. Depth of discharge means that the level, if the battery is 100% capacity fully charged and you begin to discharge it, you don't want to discharge it below certain level. Okay. Yeah. So that's what we call depth of discharge. So for most lead acid batteries, I mean, 50% is typical for most lead acid batteries. You don't want to discharge them below that, so that you also prolong the lifetime of those batteries, their cells, prolong their lifetime, so that's what we call depth of discharge. So you need to also put this into consideration in your calculation, because if you size the battery bank of 10,200 watt hour with a depth of discharge of 50%, what you're essentially doing, if you have to deliver to the load, what you're essentially delivering is half of this, which is 5,100 watt hour. But we don't want that. And I think in these issues, this is where some design begin to get problems. Okay. So now the battery size will not be given, considering this depth of discharge, the battery size will not be given as the usable capacity, which is 10,200 divided by that depth of discharge. Okay, so you're almost doubling the size of that battery. So if we look at the depth of discharge, our battery size would then be 20,400 watt hour. So that we can always discharge 50% and not go below 50%. Now, typical for lead acid battery, if you're going for lithium ion battery and some other technologies, you could go higher. For lead acid, for lithium ion batteries, you could even go as much as 95, 90, depth of discharge, because they have this higher tolerance, their cells are stronger, right? Okay, so this is what the size we have, considering the depth of discharge of 50%. Now, let us look at battery. Now, this is the battery size that you need. When you go to the market, you see different kinds of battery ratings. You need different kinds of battery technologies. Let us try to understand what how you rate your batteries. Okay, so when you go to the market, you actually see battery ratings in voltage. You can see 2 volts, you can see 12 volts, you can see 24 volts battery, right? And then you see the amp hour. Amp hour, that is the current over time, right? You can see 200 amp hour, you can see 100 amp hour, depending. So those are the things you see on your battery. So how do you now, based on this value that you're seeing on the battery, how do you now transform this into watt hour that the battery can hold? How do you know that, okay, this is actually the number of watt, because you want to be able to size a battery to provide 20,400 watt hour. So how do you know one battery? How do you know how many watt hour is in one battery? That's what we try to establish here, okay? So if you want to do that, it is, of course, we know that power is equal to voltage times time. Voltage times current. Okay, voltage times current, but that is apparent. That is in kVA. Only when you now add power factor, that's when it becomes an active power. Okay. If we make so energy, what we're actually driving at is the energy content of the battery. So energy is equals to, right, power times time. That is, power is equal to voltage times amperage times time. That is then times time, which is energy. If you do that, you have your watt hour. Okay, that's what we have, watt hour. Now, amperage is A, time is H, right? So this current times time is AH, correct? So if you replace this, if you replace this current times time with AH, then your energy will become voltage times amp hour, which is what you have in your battery, voltage and amp hour. If you multiply these two things, you get the energy content of a battery storage system. Okay, so let's just move ahead. Now let us do a sample of a sizing system. So calculate the number of batteries required in a 24-volt system. Now, emphasis on 24-volt system. I'll still come back to this 24-volt system because system voltage and battery voltage are not the same. And that's why I want us to put emphasis on this 24-volt system, 24-volt system voltage, right? Now, calculate the number of batteries required in a 24-volt system to produce 3.4. Now, this is our daily energy requirement for this client, correct? 3.4 kilowatt hour of daily energy need plus 2 days of autonomy. That's for cloudy and non-sunny days, using lead acid batteries with the following rating. Now, this is the ratings of the battery. This battery is 12 volts, 200 amp hour, and the depth of discharge is 50%. So let us use these characteristics of a battery to determine the number of battery that we need to purchase to meet this client's the client's need. So that's the calculation that we're going to do. So the daily energy need is 3.4 kilowatt hour, correct? And we have 2 days of autonomy, making it 10.2 kilowatt hour. So actual battery size at 50% GOD will now be this 10.2 kilowatt hour divided by 50. That is 0.5, 50%. That will double the size of the battery to 20.4 kilowatt hour. So we need to size this battery to be 20.4 kilowatt hour to be able to deliver 10.2 kilowatt hour on daily basis. Not on daily basis, for 3 days anyway. That's 1 day plus 2 days of autonomy. So now we want to do this. We want to know the specific storage capacity of one battery. Now, one battery is 12 volts, is 200 amp hour. So the energy holding capacity of this battery is the voltage times amp hour, which is 2,400 watt hour or 2.4 kilowatt hour. So one battery will hold 2.4 kilowatt hour. So we now want to know how many batteries do we need to have to be able to arrive at 20.4 kilowatt hour. So we divide 20.4 kilowatt hour by 2.4 kilowatt hour, and that will give us 8.5. So we need 8.5. Of course, you don't have half battery. So you have to either add it up, approximate it to 9, correct? But here is the problem. Our system voltage is 24. So what that means that we're going to add 2 batteries to arrive at system. So we're going to combine 2 batteries to get to 24, correct? 12 volts times 2 is 24, right?
Yes.
So we need to pair 2 batteries to get to 24. So you cannot have 9 batteries in that system. You must have either 8 or 10. Okay.
I'm trying to wrap my head around that, please. So
okay, what exactly are you now? this is the point where I said that we need to give attention to battery voltage and system voltage. We are still going to come to a point where you arrange batteries in series and parallel. Okay, in series and parallel. So we add batteries in, now the system voltage is 24 volts. This 24 volts is what is going to go into your inverter. So when you're looking at inverter, you might look at inverter that accommodate 24 volt input. However, your battery voltage is 12. So to arrive at 24 volt, you need to pair two batteries in parallel. No, sorry, in series. Okay, you need to pair two batteries in series. Correct? Am I right?
Yeah, go ahead. Go ahead.
Yes, in series now. You're correct.
Exactly. So you need to pair two batteries in series. Sometimes it can be a little bit complex. You need to pair two batteries in series to arrive at 24.
Yes, now that is series connection you add. When
Exactly.
Yeah.
So yeah, to arrive at 24 volts. I want us to follow this, please. So we need to add it to arrive at 20 because of our colleague that says is trying to wrap it. So I'm trying to do a further explanation to this, right? And it's a little bit tricky here. You need to pay attention to this. Your system voltage and your battery voltage are different things. So you may have a system that has to, no. Now let me make it this way. If you have a system that requires 48 volts, I have 12 volt battery. How many battery do you need to arrive at that 48?
You need 4.
Two.
You need to put 4 batteries in series.
In series, yeah.
Yes,
to
4.
arrive at that 48. I want us to be clear on this. And when you're looking at your inverter, make sure you have the size, the right size of inverter that can take that voltage. Otherwise, you blow up the system or your system will not work. Look for inverter that can have. Now, when you get an inverter, look at the input voltage and make sure your battery voltage corresponds to the input voltage of that inverter. So this is where you begin to do your pairing of batteries. If it's 24 volt system, you have to pair 2 batteries. If your battery is 12 volt, you have to pair the 2 to get to 24 volts. If it's 48 volt system, yeah. In fact, we've seen batteries that are 2 volts. Okay, so you need to keep pairing until you get to the required system voltage. Then every other thing becomes in parallel. We are going to get to series and parallel connection, but I think what we're going to talk about is for PV panels. But it's the same principles.
Before then, I have a question.
Okay,
sorry.
Please.
I want to know this DOD, depth of discharge.
Okay.
How can one get that information from a battery?
How can you get direct information? Okay.
And this 10.2 kilowatt hour, what do you call it, autonomy? Okay. Is it the same for all types of batteries?
So, first of all, you say how can you measure the depth of discharge in batteries? That's the first question you asked.
I didn't say to measure. How can one know if you buy a battery? Sometimes it's not stated there on the battery. How can you know the DOD? So that will help you.
So sometimes this is discretionary. Sometimes if you look at the technical sheet of the battery, you will see it there as well. You will see now when you look at the tech sheet of batteries, these are the things you might likely see. One of the things you will likely see is the number of cycles that battery can go. Number of cycles means that the number of times you can charge that battery, you can fully charge that battery and discharge that battery. After that number of cycles, the battery it will reduce. Sometimes it will reduce to maybe the capacity of that battery will reduce to maybe about 80%, depending. But you're going to see this in the tech data sheet of a battery. The number of cycles. Lithium ion battery, I think I've seen lithium ion battery that go as far as 6,000. For lead acid battery is low, it's much lower, maybe about 1,000, 1,005 is much lower. But for lithium ion battery, it can go, some of them can go as, depending on the quality of the cells, some of them can go as high as 6,000 number of cycles. So these are the kind of things you see on the battery. Now look at the idea. So if you have a battery that has, for example, let me for illustrative purpose, if you get a battery that have 100 number of cycles, 100, it means that you can charge that battery fully and discharge it only not 100 times. After that, the capacity of the battery might reduce to 80%. Okay. Now, if you decide to charge that battery at 50%, what you're actually doing, instead of the number of cycles to be 100, you increase that number of cycles to be 200. So you extend the lifetime of that battery. I don't know if this makes sense. I mean, I hope I'm not creating more confusion here.
No, yeah, right. It's okay. Yeah, makes sense.
Okay. Yeah. So there are different techniques, and that's why these things are called design. You know, designs are not cast on a rock. You know, it has to meet specific need. It has to meet specific budget. So there are so many specifications. So if you have this knowledge, you can actually play around your design. Okay, what's the system capacity? What kind of battery technology? What's the depth of discharge I can recommend? Now, battery depth of discharge are programmed in your battery management system. Okay, they are programmed. Some of the inverters allow you to do this programming. You program it. So this is the way you raise the hand. Hello. Yeah.
We can't hear you.
We can't hear him.
Okay. Because he raised his hand. So this you need to understand this variabilities to be able to play around your design. Okay. So so far where we have a depth of discharge of 50%, and we divide. Oh, okay. Where are we exactly? Okay, so I think we are done with this. We are done with this slide already. So we have either 10 or 8 or 10 number of batteries.
Yeah, the second one, I was asking whether the autonomy is the same for all types of batteries.
No. The autonomy is
the 10.2 kilowatt hour.
No, 10.2 kilowatt hour is just now is based on discretion of your client and budget of your client. Some people might just do 1 day of autonomy. Okay, so the 1 day of autonomy.
No, I think Chima, the 10.2 is based on our example.
Yeah, exactly.
Data we have for our example.
Okay,
you can have a different data for another example, another client. This is what we generated from. If you go back to the beginning of that first table, so that's why we arrived at this with the 2 days autonomy. We arrived at 10.2.
Yes.
And somebody asked a question, why multiply by 3 instead of 2? I think it's all wrapped around the same issue. First of all, our demand was 3.4. And then we added 2 days for autonomy. Those 2 days will be 6 point something. So I think if we started from the beginning, I mean,
there is no issue. How do you get this? How do you arrive at that 10.2? Maybe in a new installation. How do you establish that 10.2 or whatever figure for the autonomy?
No, if you're able to, sorry, sir, the presenter, let me say something here. If you're able to establish your first demand, which is 3.4, it is now left for you to say you want to add 1 day autonomy or 2 days autonomy or 3 days autonomy. When you do that, you multiply by that number you've added. That's what you are doing.
Okay, it's an assumption.
Yeah, this is an
assumption.
This is based on question here.
Yes.
Sorry, let me come. I think some of our colleagues just came in. They were not here when we started, and that's why.
Oh, yes, that's the problem. Maybe you don't need to refresh.
Exactly.
You don't do a refresh.
Yeah. So please, because of time, this is being recorded. Yeah, you're going to the video is going to be.
I have one more question, please.
Okay,
so with the current discussion, we're looking at 24-volt system. So we're looking at 8 to 10 batteries. So automatically, using 12 volts battery, we have to put it on parallel. Is it what's the conclusion?
If you push now, two is going to go in series, and then 8. I mean, two to that is if you're using 8 batteries, then you have to put 2 in series to get 12 volts, and then you have to do 4 pairs. 4 pairs that's 4 pairs in parallel, 2 pairs in series.
Okay.
Yeah, Chima.
Yes, please.
Just for benefit of doubt, I know we want to cover ground, but this is basically what everybody has gathered here to understand.
Sorry.
Basically, can you hear me?
I can hear you. What?
So if you need to just look at your population, started with 13 people. If you're having up to 25 for now, I might request we just recap it again so that everybody will be on the same page. Because once you don't get it from the beginning, you're going to struggle through. You're going to struggle through.
I totally agree with you, but again, we have a time slot for this, and if we go back, we are not going to cover what we need to cover today. And what that means, we're going to extend the number of Saturdays for this training.
We'll not be able to pay extra.
So that's the challenge. Okay. But let me just do a quick one. Let me just.
That's on that table, that festival alone. So this
is where we started from. This is where we started from. Place. This is our demand. This is the electrical load that we want to size. Okay. We have television, fridge, light bulbs, and standing fans. The demand is 410. The energy requirement per day is 3,400 watt-hour or 3.4 kilowatt-hour. Then we started by sizing the inverter. We did the calculations for the inverter, and I said that calculation for the inverter is based on the power demand, based on this power demand. Okay, we have a load factor of 70% and a power factor. If you need to convert from active power to apparent power, which is the rating you find most inverters in the market, you need to then divide by the power factor to arrive at the apparent power. Then we did an exercise, and then we get to the battery system. Now, from that load characteristics that we see already, we already know that our daily demand is 3,400 watt-hour. And we assume days of autonomy to be 2 days. So if we add that 2 days to our normal regular day, it becomes 3 days. And that's why we are multiplying this battery size by 3. And we will do that multiplication. We'll have 10,200 watt-hour.
I don't call you, know the work for you.
Sorry?
I'll call you severally.
If you are not speaking, please mute.
How far? I just spoke with this and that standing there.
For muting everyone. Okay, so let's continue from where we stopped. So we have already established that we have the battery that we have is going to be 10 or 8 or 10, 2 in series, 4 in parallel to arrive at our system design. So here's an example. Here's exercise number 2 that I want us to do. Now calculate the number of batteries required. Now we are going to change some variables here. Instead of 2 days of autonomy, please assume 1 day of autonomy. And we are going to use lithium-ion battery in this case. And our depth of discharge is 80%. Now the battery characteristics is 12 volts, 100 amp hour. So let us calculate the number of battery required for this new setup. Our load is the same. I mean, the load is the same. Daily energy demand is 3.4, but in this case, we are doing only 1 day of autonomy. 1 day of autonomy, sorry.
1 day of autonomy.
Yes, please.
That's 3.4 now.
So that's 6.8. 6.8 divided by 0.8. Okay. Yes. Good morning. How are you?
Do we have answers already? These are basic. These are just basics. Just follow the step that you can already see on your screen, and then you'll get your answer.
Yeah, you need 2 batteries of 12 volts. You need 2 batteries of 12 volts, 200 amp hour, connecting 2 of them in parallel.
So the question is, what number of batteries do you need for this? We are not even asking of the configuration already at this time. Just how many batteries do you need? You have to know the number of batteries that you need first.
You need to, okay, sorry.
You need how many? Please follow the steps I have already presented in this worked example.
Getting 4 batteries. 4 batteries.
Please look at the battery characteristic. This battery is 12 volts. It's 100 amp hour, not
100 amp hour. Yes, 100 amp hour.
Yes.
7.
So what this means that the battery capacity is even less.
Yes.
Yeah.
Yes, it's much less. Okay. So yeah, the mistake I made was using 200 amps. So making that
and your depth of discharge is 80%.
Yes, it's 80%. Yeah. Yeah, it's 80%. Yes.
We need 7 batteries.
Yeah, you need 7.
That's
You can't
7
have 7, so
batteries.
you need 8.
So of course, well, yeah.
You need either 6 or 8, since you can't have 7 batteries in the arrangement.
Exactly. So is anybody getting something? When you do this calculation, you will get 7 batteries, but of course you need to do 8 batteries.
Yeah.
So
yes, 8 batteries.
Okay, correct. So I want to believe that we all understand it. So this is how you size your battery. Depending on, now you need all this battery technology to be able to do this calculation. You need to know what depth of discharge you want your battery to go, what is the voltage of the battery, what is the amperage of the battery. Then you can then do this calculation and then size your battery. Now we've sized the inverter, we've sized the battery. Let us size the PV array, the solar modules. Now using the example of the load that we already have from the previous example, now we are required PV energy output is 10,002. Now when you're sizing your PV based on the energy demand, not on the power. If you go back to this table that we have, your inverter is based on power demand. Your battery is based on energy demand. Your PV is also based on energy demand. Okay, so let's go back to the PV. So your PV is based on the energy demand, and your energy demand is also with 2 days of autonomy. So we're still dealing with 10,200 watt hour. That's 1 day plus 2 days of autonomy. So we want a PV system that will be able to produce this energy on a daily basis. On daily basis, we are still going to criticize this our design actually, but on daily basis, this PV will produce this. Okay. So how do we size that? Now let's make an assumption. When you're doing your designs, there are always assumptions. And in your documentation, please clearly state your assumptions. When you're doing documentation, clearly state your assumptions. Okay?
So is this peak sunlight hours, is it based on like annual? So whatever the season of the year.
Sorry, say that again, please.
Is it like an annual average that takes into account all factors of seasonality?
What value is it? The 5 hours?
PSH, the PSH, yes.
Okay. In our first class, I explained what the PSH is, and I talked about in Nigeria. So in Nigeria, it varies. If you're going towards the northern part of Nigeria, it is safe to assume 5 hours. At maximum, you can do 6 hours if you're going towards the northern part of Nigeria because you have more sunshine in that region. If you're going towards the southern part of Nigeria, it is safe to assume 4 or 4.5, at maximum 5. In fact, I can't even recommend 5, especially if you're going to south, right? So it varies. If you go to some other countries, so you might look at internet to see what value for a particular region might give you. Okay, so it's not a one size fits all.
Okay, thank you.
Yeah. So in this case, we assume 5 peaks. And I also explain what is peaks on hour, because I know I've had this, when I say 5 hours, somebody tells me that no, you can't say 5 hours. The sun comes out in the morning as early as 8 o'clock and it stays until 5. That's more than 5 hours. And I said, no, that's not what we mean. That's what we mean by peak sun hour. Is a technical terminology for sizing PV systems. Okay, if you don't understand it, please refer back to our first video and you'll be able to clearly understand what this means. So we assume 5 peaks on hours in this our sizing. So now the PV size is, so you have to divide the required energy output by this peaks on hour, which is 5. So when you do that division, you have 2040 watts. 2040. Now this 2040 watts is the size of the PV system that we need to produce this energy in one day. But this 2040 watts is based on standard test condition. I explained all of this in our first class on solar systems. It's based on standard test conditions. So that at the manufacturer's label, after they have subjected this PV to standard test condition of 1000 watt hour, 1.5 air mass, and then what's the other one again? 25 degrees centigrade. At 25 degrees centigrade temperature, they obtain this value. However, the condition in which you're installing this PV will not always be at that standard test condition. It can be higher, it can be lower. So there will be losses. So this your PV system will not always provide or produce 100% energy of what it was labeled. So you need to also include your losses in your design. These losses could be as a result of variations in the standard test conditions. It could be as a result of cable losses and so many other things, right? So this is your output from your PV system at standard test conditions. So you need to include your losses. So let us assume that there's what called performance ratio. I also explained this in that video. Performance ratio. So performance ratio is the deviation the actual performance of your PV system from the designed or the theoretical value. Okay. So in this case, you're going to assume a performance ratio of 75%. 75%. So we assume that 25% of the design value will not be realized. So we're already going to get about 75%. And this is even more, in some cases, this is more optimistic. This 75% is an optimistic value in some cases. In some cases, you might just want to do 70%. Okay. But 75% is a good point, is a good assumption, right? Now, if you assume 75% of performance ratio, then your actual PV size will now be your size at standard test condition divided by the performance ratio. And if you do that, you have 2,720 watts. Now, 720 watts peak. But anytime, most time we'll talk about PV array or PV system, we have to represent it in peak. That is 2,720 watts peak. So this is the size of the PV array that you need to produce 10,200 watt hour based on the assumption of 5 peaks on hours and performance ratio of 75%. I hope this is clear. Okay, so now we've successfully sized the PV array. So let us do another exercise. Now calculate the PV size if the required energy, in our own case, we did, in our own worked example, we did 10,200. But I'm asking you now to resize that PV system if the required energy is 20,400 or 20.4 kilowatt hour, and assume a peak sun hour of 4 and a performance ratio of 70%. Please let us rework this with these new variables.
So you'll be getting 7,285 watts.
Is anyone getting something different?
All right.
Okay, so I assume that we all get this. You're going to have 7,285.7 watt peak of PV system with this new characteristic or this new variable that we've introduced. Okay, fine. So let's move on. There's another thing that we need to size.
For all the panels, this is for all the panels involved.
Yeah, for all the
That's
panels,
what
of course,
you
this for all the
jointly
panels involved.
contribute. Okay, thank
This
you.
for all the panels. So, for example, this, if you go to the market, you can have 400 watt panel, you can have 300 watt panel. It doesn't matter. What matters that you make sure you combine all of this wattage to make sure you get up to this value. Okay. So it depends on the size of panel you find in the market. You could go to the market and you find 600 watt panel, then you're going to have lesser number of panels. If you go to the market, you find 300 watt panel and it's affordable, then you're going to get higher number of panels to arrive at this required capacity.
Okay, so more like I'll divide and then thank
Exactly.
you.
So divide this by the number of panel the capacity of the panel that you find in the market.
Of the panels, yeah.
Yeah, then you know the number of panels that you buy.
Number of panels that you need. All right.
Okay, yeah.
Thank you so much.
Okay, in addition to that, what of the panel comes in voltage? So how do you, in selecting the panel, you have to also consider the voltage of the panel?
Yeah, the panels they come with the electrical characteristics. We are going to get to that. We're going to get to when we are talking about series and parallel configurations of panel. We're going to talk about that, please. Okay, thank you for bringing that up anyway. So there's one more component that we need to size, which is the charge controller. Okay. Now let me explain what the charge controller do. It's on the hint side for a lot of people who are not technical. They see panels, they know panels, they see inverter, they know inverter, they see battery, they know batteries. But there's something in the line that is not too obvious, but very, very essential. Now your solar PV panels, your solar PV modules, they produce current, DC current. Okay. Now current is made up of voltage and current. So they produce this. Your PV modules, they produce power. Sorry, not current. They produce power. That is voltage times current, right? Now, this power comes at certain characteristics, at certain voltage, it comes at certain current. However, your battery needs a certain voltage to charge. If you have a battery voltage of 12 volts, it is possible that sometimes the power from the solar panel could be coming at a voltage that is higher than this battery. It could be coming at a voltage that is lower than this battery. But this battery needs 12 volts to charge. Not 13 volts, not 10 volts. It needs 12 volts to charge. So what charge controller does? Charge controller conditions the power. It kind of converts current to voltage to make sure that this power that is coming into this battery is maintained at a 12 volts. Then the current can vary. The current it can convert from current. So if the voltage that is coming in is lower than 12 volts, it can convert the current into voltage and increase it to 12 volts and push it into the battery. So in that case, the current will be reduced. If the voltage that is coming in from the panel is higher than 12 volts, it can reduce it. It can reduce the voltage and push it to current and allow 12 volts to go into the battery. So what charge controller does is that it regulates the voltage of the battery, the charging voltage of the battery. It makes sure that the battery remains at its specified voltage. If your battery voltage is specified at 24 volts, that's your battery voltage, not your system voltage. If your battery voltage is 24, your charge controller makes sure that 24 volts keeps going into that battery because it will damage the battery. If you go above 24, you damage the battery. If you go below, you also got to damage the battery. So charge controller maintains that constant voltage that goes into the battery. So that's what charge controller. If you remove that charge controller, then you blow up, the battery is going to damage. So that's what charge controller do. And that's why it always comes in between the solar panel and the battery. If you don't have a battery system, if you have a design that does not have a battery, then you don't need charge controller. I say that again. If you have a system that does not have battery, then you don't need a charge controller. Okay? So that's what a charge controller do. Now let us look at how to size.
But Chima, hello Chima.
Yes, please.
Does it go with the lithium battery too?
Yes, they're all batteries. Yes,
the hybrid unit.
Oh, the hybrid what?
The hybrid unit. Hybrid.
When you say hybrid unit, what hybrid are you talking about?
When you have those components assembled together.
What component and what components?
The battery system. It comes in the hybrid.
So when you have
that's charge controller.
Yeah,
complete package.
You mean charge controller and the inverter?
So there's some charge controller that has in. Okay, go on. Someone is speaking, please.
Like the system I currently run just has the batteries and then of course the inverters. I don't have a separate charge controller.
So what that means is that the inverter has charge controller inbuilt. Now some inverters have inbuilt charge controller. So when you're looking at inverter, please look out for this. Look at the specifications, and that will already tell you the capacity of the solar panel you can feed into that inverter. You don't go beyond that, otherwise you also damage your system. And so to allow you for some certain level of flexibility, you might just have a separate charge controller so you can, scale up and scale down of your panels. But
that's what the guy recommended. We need as an additional charge controller, which I got until we improve the performance.
Exactly. So if you have an inbuilt charge controller in the inverter, it already limits the capacity of the solar panel you can feed into that inverter. Okay. So let's continue. Now we are still calculating size or sizing charge controllers. Now our battery voltage in this case is 12 volts. Okay, 12 volts, and then our solar PV array is 2,720 watts. Okay, so all we need to do is to divide this PV array by the voltage, the PV size by the voltage. So if you divide 2,720 by this battery voltage, you get your required charge controller size. So in this our own case, our required charge controller, the size of our required charge controller is 226 amps. Charge controllers are rated in amp, that is in current. That is the amount of current that they can, they can handle, right? So that's how charge controllers are being rated. So in this case, please look, we are also assuming that other losses are neglected in this our own case, because when you're sizing this system, there is something that I didn't talk about, but also important that as engineers, we also look at them at some time. So when you charge a battery and discharge a battery, the amount of energy you put into that battery, you don't get 100% of that energy back. There are losses, there are conversion losses. Okay, so and that's why when I do this, you can assume that losses are neglected. And those are the kind of losses I assume that are neglected. But in realistic cases, there are conversion losses, please. So for example, Chooks, you raise your hand, but before I allow you to speak, let me land on this point. There are conversion losses. So in some cases, it might be 95%, meaning that you're going to lose 5% of the energy you put into that battery, and when you're getting it back, you might lose 5%. So you also need to pay attention to some of this thing when you look at the technical data sheet of this equipment. Okay, so Chooks, you raise your hand. Can you go on, please?
All right. So based on so we've been able to determine what the sizing of the charge controller is going to be. So, but my question is, when you talked about the solar PV and all of that, are you going to see a charge controller that has this sizing, or you are going to probably calibrate it to be able to handle? So what do you do with this information for the the solar charge controller? What do you do with it?
Thank you very much. So you will not go when you get to the market, you're not going to see a charge controller of this rating. In most cases, you might see 60 amps, you might see 80 amps. I mean, in that range, right? So you have to do a combination of charge controllers to get to this. Okay, so
in this case, so just to at least to make it more hands-on.
Sorry?
No, I mean for what we have now. So what would your recommendation be? Just give us like a.
So for example, if you have 60 amp charge controller, you're just going to divide 226 by 60. Okay, and then you need about 4 charge controllers for this design.
All right, I see. Okay,
all right, thank you
very much.
Okay, so now note that I want us to also understand something. Know that increasing the battery voltage will reduce the capacity of the charge controller. So sometimes if you want to manage cost, you might go for a higher battery voltage. If you go for a higher battery voltage, what that means that you reduce the required charge controller. So in this case now we have 12-volt battery, right? Imagine that we have 24-volt battery. This charge controller will be reduced. If you divide 2720 by 24, you have a lesser number of charge controller, capacity of charge controller. So increasing the battery voltage will ultimately reduce your required charge controller. Okay. So now this is the summary of our design. So we've been able to size all the equipment in this system to meet the load, right? So this is the summary of our design. So you need 226.7 amp charge controller. I mean, it's going to require to support 2,720 watt solar PV array. And try to move this. So PV array, and of course, to charge a battery of 10,200 watt hour. Okay. Now let us do some level of criticism to this our design, because sometimes it's also good to criticize your work. It's very, very important, right? So to do this, okay, there's an exercise for us to do before we move ahead, please. I always like my colleagues also try their hands on few exercises. So let's complete this exercise number 4, please. So calculate the required charge controller for exercise. That's the exercise that you did, not this exercise, the one you did, exercise number 3 that you did, that you will arrive at 7,285.7 watts PV array. Okay. Calculate the required charge controller for that exercise, assuming you have 24-volt batteries. Please, let's quickly do this. Tunde, you raised your hand.
Yeah, please, thank you. Yeah, I have a question on designing practically.
Okay.
Now, when you made mention of assuming other losses are neglected, so how can we design accommodating all the other losses in order not to fail, not to be look like somebody that doesn't know how to design in the real practical life? That's my question. So how can we accommodate other losses, because there is no way that we won't be getting any other losses. How can we accommodate all the losses in the real practical design? Thank you.
Okay, thank you for the question. Let's conclude on this exercise and I'll answer your question. I'm sorry. So let me see, how many people have been able to finish this exercise number 4, and what do we have?
303.57. Yeah.
Okay, correct. So we are all correct. Now to address Tunde's question, Engineer Tunde's question, let me go back to any of the system. So for solar PV arrays, okay, because your question, in solar PV designs, we assume all the losses, to have been taken care of in this performance ratio. That's for PV system. We assume all the losses to have taken place. That's the line losses, the losses in your wires, the losses in your PV system because of temperature differentials, solar intensity. We assume all the losses have been, and so that's what performance ratio is. Performance ratio is actual performance compared to the theoretical design. That is your manufacturer specification. So for solar PV, we assume that all the losses have been taken care of. That's why we use 75%. If you feel that the losses could be more, they can reduce this further. Now, in your design system, when I was talking about performance ratio in the other class, I said that performance ratio, you cannot determine performance ratio ahead of time. No, it's always an assumption. But it's good that after you've done your installation and your PV has worked for some time, maybe 6 months or 1 year, you can now go back and determine the actual performance ratio. So how has this PV performed compared to the theoretical values? That's when you can now, okay, this actual performance ratio of my installation. Yeah. Then you can then compare that with your assumption. That will also improve your knowledge of the system. This is how you keep building your knowledge and capacity in the solar field, the solar industry. Okay, is somebody saying something? Okay, let me talk about batteries. Because I know when I talked about battery, I also assumed that maybe some of the losses, and I talked about cycle losses. I mean, when you charge and discharge, there are losses. why I say this are negligible is that they're not significant. It can be maybe, like I said, it can be 95%. So just about 5% losses, right? So they're not also much. In some cases, it might be just about 5. I mean, just in that range, about 5%, right? You can only know this for sure when you have tested, when you have deployed your system and you actually take readings. Now, there are factors that affect these losses. Let me also, so these are not cast on a rock, but you need to put on your thinking cap to actually estimate, the level of loss. So let me give you an example. If you have a battery system that is installed in a high temperature region, if the temperature of your battery storage is high, then you should anticipate more losses. It's just science. And that's why battery manufacturers will tell you that if they tell you that this battery, the lifetime is 6,000 number of cycle, they will tell you the temperature that can happen. They will tell you it's usually 25 degrees. And so what that means that if your installation is maybe 35 degrees, where you install those battery system, then you should expect more losses and you should expect lesser number of cycle. That's what it means. So if you look at the battery technical data sheet, and that's why sometimes you cannot, that's why it's called design anyway. You need to also put so many things into consideration to come out with a system that works. And that's why it's very important that we understand this. And I think this is part of the reason why some installations are failing, because people who don't understand this and go into this and they do these designs and they do installations and it's messed up, or it doesn't work, or it doesn't meet the requirements. If you're installing I'm sure most of us who have seen battery installation where you have to put an air conditioning system to maintain the temperature. Whereas in some cases, you see battery installation that are exposed to, high temperatures without any temperature control. So in that case, you expect more losses compared to a battery installation where you have controlled temperature. So this is so they're not cast on a rock, but like I said, give or take, if you have taken measures to limit these losses, you should expect something about 5%, maybe charge and discharge losses. And that's why in some cases I say that this is just, I put them as negligible because it depends on the prevailing conditions of your installations. So I don't know if that's clear in a way.
Yeah, thank you. At least I picked one or two things from what you said now. Thank you.
Okay. So now let us criticize our design. All those times we are talking about number, but let us put them in a practical, let's put them in a certain configuration. So every calculation we've done so far, I've just tried to represent them here, okay? So this is our house. Our power demand is 410. Our daily energy need is 3.4 kilowatt hour. They will have a solar panel that can produce 10.2 kilowatt hour per day, okay? We have a charge controller of 227 amps charge controller. This is our battery storage. Our total capacity is 20.4, but our usable capacity for 3 days is 10.2 kilowatt hour, right? Now, this is our inverter size, 586 watts, okay? So this is our design actually. So now, everything here is DC. This current here is DC, here is DC, here is DC. Inverter converts DC to AC, and it fits into the house, okay? Now, I want us to look at this. Our daily energy need is just 3.4, but we have a system that can produce 10.2 on daily basis. So what that means that if we produce 3.4 that we need for the day, right? And maybe our battery is filled up, maybe it's produced another 3.4 to fill up the battery. Okay, of course, our battery will already be full at 20.4 kilowatt hour. Now, after this installation, it's expected that you allow the battery to charge fully before the system is commissioned to start working, right? Now, but what I want us to look at, our daily need is just 3.4, but our daily production is 10.2. So we have curtailments. We have production that are not going to be utilized because this battery will have already been charged, to meet our days of autonomy, correct? So it cannot absorb more of those energy, right? So what can we do? If you look at this design, what can we do? Do you think is an optimal design? Because if you want to implement this, you're going to actually spend more and you're going to have redundant system. What do I mean by redundant system? That solar panel will produce more energy than you need on a daily basis, and it's going to be redundant. It's going to be curtailed. What can be done? I want us to look at this. I just want us to think about this. I don't want to be. I'm presenting this as a problem, and I want us to think about.
We can reduce the autonomy because we designed this based on 2 days autonomy.
Yes.
We can reduce the autonomy to 1 day.
Okay, that's a great way to do that. Exactly.
What if we increase the amount of time it takes to charge, so that we don't need this much capacity of panel array, so PV array?
If you increase the amount of time, remember, on daily basis you have this amount of. So even if you say if you increase the amount of time it takes to charge the batteries, or what is that what you're saying?
Yes, so that you don't need to engage this much investment in the PV array.
But you don't control sunlight. In your design, you already have five peak sun hours, so you don't control the sunlight to increase that, right? So you don't have that control.
Okay. So you are faulting this point of view, right?
Yeah. So now sometimes when we go to meet the if there's money to implement this and the client is comfortable, fine and good. But again, sometimes let us look at it. If there is an alternate supply system in that building, now this is ideal for a standalone where there is no grid at all. If there is no grid, then and there is need for the system to stay on for additional 2 days. So if this is a critical, so for example, if this is a critical facility, then this may be recommended. Again, you might also look at, okay, why do I need to oversize my solar panel? Because I want to make 2 days of autonomy. Can we bring in generator if there is no grid? Is it cheaper? I mean, because these 2 days of autonomy, the reality is that these 2 days of autonomy, it can occur, but not something that occurs almost on daily basis. It can occur maybe 2 or 3 times in a year. But you don't want to keep this oversized system because of those, occasion that rarely happens. And this happens during rainy seasons, correct? During dry season, it rarely happens. It cannot. So why do you want to size this for a whole year round? Is it possible to bring in generators for those 2 days of autonomy? You look at the cost comparison. Are you going to spend more than you're going to spend to do this additional excess capacity? So this is where you put on all of your economic and technical thinking capabilities and thinking cap. What could happen? How can you? So you present the different scenarios to your clients. Okay, if I oversize the system, this is what it's going to cost you. But if you decide not to oversize, you can use generator. This is what it's going to cost you just for those rare occasions that 2 days of autonomy could happen. You can just use generator, no problem. It's fine. Okay, this is what it's going to cost you based on fuel and whatever it is. You put all those things together. Alternatively, if there is grid, you can say, okay, if there is grid, which means the grid can actually come in, charge the batteries for those 2 days of autonomy. You don't need to charge it from your solar panel. Remember, your battery needs to be charged from any source. It must not be from solar panel. But the point that you need to have that energy storage for the 2 days. Where that energy storage is not available for the 2 days, what can happen? Can you bring in generator? So you just need to think around all of this. So in this case, this is what I have also done. If there is grid in this system, then we can reduce this solar panel. We can reduce to even 1 day or even no day of autonomy. If there is no sunshine for that day, maybe perhaps this grid would have charged that battery for those 2 days of autonomy. You don't need to charge from the solar PV. I don't know if this is making sense.
Yes, it makes sense. That with this what I have in my house, the grid support.
Okay, so
I don't have autonomy.
But if that is the case, please, you're going to need a hybrid inverter. What do I mean by hybrid inverter? Some inverter could be hybrid in the sense that they have charge controller, but ideally hybrid inverter actually is that they can take AC and charge your battery. So they have rectifiers. Okay. So it's like a two-way inverter. So in this case, you need the hybrid inverter to be able to charge this battery. So this inverter can take AC, convert it to DC and charge your battery. And it can also take your DC from your battery, convert it to AC and push it to your house. So in this case, you need a hybrid inverter. Okay, but if you don't want this case, you can just do a battery inverter in this case. I mean, in which case you're just doing one-way conversion from DC to AC. But if you're bringing in this one, then you need to also consider, so you need to also understand the architecture of your design to be able to recommend the kind of equipment, PV inverter that, I mean, the kind of inverter that are needed. If you go to the market, you see different kinds of inverters. You have inverters that have solar charge controllers inbuilt. You have inverters that are hybrid, meaning that they can take from the grid and charge your battery. I have inverters that are just one way, just normal inverter, which only one way from DC to AC. They can't do the reverse. So you need to know what you want and the right specification of equipment to use. So this is just, like I say, sometimes it's good to criticize your design so that you don't go and look like unprofessional in the face of it. Just always play different scenarios of things that could happen with your design. Okay, and when you speak to your clients with all of this in view, your client will be more justified that you understand and you know what you're doing. And you also leave your client with more options on what to decide, how to, what system to implement. But it's good to present all of these options to your client. So now let's also look at the series and parallel configuration of solar PV. I hope we'll be able to finish this in less than 30 minutes. Series and parallel configuration of PV arrays. Now, we know that you have modules, and when you have modules, you connect them, you form what we call PV array. Okay. Now, when n number of PV modules are connected in series, the entire string of series connected modules is known as the PV module string. PV module string. Okay. Now, the modules are connected in series to increase the voltage. Remember when we were talking about the battery, and I told you that if you have two batteries of 12 volts and you want to achieve a 24-volt system, you need to connect two in series to achieve a 24-volt battery system. The same thing is applicable to PV systems. Okay, so your PV systems are, somebody was asking about the voltage of PV systems. So it varies. So you have to look at the technical data sheet of your PV system. It can be 12 volts. It can be 5 ampere, it can be 7 ampere, it can be 8 ampere, it can be 9, just in that range, about 9 amperes. So depending, right? But what matters most is your voltage. How do you arrange them? How do you configure them to get a certain required voltage? Because your equipment operates at certain voltage, right? Your inverter operates at a certain voltage. So you must arrange your PV system to meet that voltage, and also pay attention to the input current, so that you don't combine your PV so much so that you go beyond the input current that is required for your inverter. So it's important that we look at all of this technical data sheet and adhere to their specifications. Okay. So to increase current, if you want to increase current, okay, remember that voltage and current is equal to power. So if your system has been specified to be 24 volt and you meet that 24 volt, but you want to also increase the power, you can no longer increase the voltage. Remember, the voltage is already 24. You cannot go beyond 24 volts. But if you want to increase the power, what you need to do is to increase the current, keep increasing the current until you get to the required power that you need. So this is just to illustrate that. So now this system is connected in series. Okay, so when you connect them in series, you're increasing the voltage. So you have 3 systems that are connected in series. So this is going to be 36 volts. The voltage of the first system plus the voltage of the second system of the second module plus the voltage of the third module, we give it at 6 volts because you connect them in series. Now your current will remain the same. Your current is 5. Remember, the current of one module here is 5 ampere. Even though you're connected in series, your current remains 5 ampere. It doesn't increase. Now your power is equal to voltage times current, which is 180 watts. Okay, so this whole arrangement is 180 watts. This 3 panel, the power output from this 3 panel is 180 watts because they are also connected in series. Now let us look at the parallel configuration. When you connect them in parallel, what you're increasing is the current, not voltage. The voltage remains constant, but you're increasing the current. if you connect them in parallel. So the current becomes the current of the first module plus the current of the second module plus the current of the third module. So 5 plus 5 plus 5 will give you 15, but the voltage remains constant. And when you multiply 12 times 15, you still get 180 watts. So whether you do series configuration or parallel configuration, it does not change the power of the output. The power of the output remains the same, but what changes is the input voltage, the output voltage and the output current is what changes, but the power remains the same. So this is series configuration, your power is 180. This parallel configuration, your power is 180. But in this case, your voltage is 12 volts and your current is 15 ampere. But in this case, your current is 5 ampere and your voltage is 36. Okay, so let's just have that in mind. I don't know if there's any question at this point. Okay, good. Now this kind of configuration is also applicable to your battery system. You know, when I was talking about battery, we talked about parallel and series configuration. The same thing applicable. If you want to increase your voltage of a battery to meet some certain requirements, you have to add them in series, okay, to get certain voltage of your input system, input design system. So this is just a further illustration of series and parallel. So in some cases, you have series and parallel configurations all together. Once you meet your voltage, once you meet your required voltage, every other layer you're going to be adding is going to be in parallel. Once you do your series connection and you meet your required voltage, you're going to keep pairing that series connection if you want to keep increasing the currents. And that's what I try to illustrate here. Now, this is a typical data sheet of a solar panel. Somebody asked me, before now, what are the specifications of this panel? So this is a typical. This is a picture I snapped from one of the panel. This panel is damaged anyway, but what matters is the specification. So this is a monocrystalline solar panel. Somebody reached out to me about the type of solar panels, and please bear in mind that we only have 3 kinds of solar panel: monocrystalline, polycrystalline, and thin film. Every other things I talked about when I was talking about solar panel, those things are just technical. How do I put it? These are just technical terminologies, okay, based on the improvement of efficiency of solar panel. So when you talk about half cut, you talk about N-type. So when I talk about N-type or P-type or P-type system, please, they are not type of a solar panel. You have monocrystalline, polycrystalline, and thin film solar panel. All of those things are just based on sometimes maybe chemical composition of the cells, okay. But in all of this is just to improve the efficiency of those cells. That's what it means. So for this panel, is a monocrystalline solar panel. It is 320 watts. So you can see some of those terminologies that we've talked about. Now this is rated maximum power. Now this solar panel is 320 watts peak output. You have the voltage at maximum power. That's what this means. The voltage at maximum power. So what maximum power means that when there is no current, like when current is 0, this is going to be the voltage. No, sorry. That is OC. VOC is when the VOC means that when the current is 0, that is open circuit voltage, right? Open circuit voltage is when the current is 0. Then this is your open circuit voltage. But this is your voltage at maximum power. That when we talked about, in our first class, I talked about what MPP means, maximum power point. So at that maximum power point, this is going to be your voltage, okay, and this is going to be your maximum power current, okay. This is what is this? 8.89 ampere. Like I told you, solar panels are just in this range, maybe 8, 9, 7 amperes, and then the voltages, okay. So this is just a technical data sheet of solar panel. And I took time to explain all of this in our first class so that when you see them, you understand what they mean, what short circuit current is. Short circuit current actually means the current when when the voltage is 0. This is going to be the short circuit current. And it's always higher than the maximum power point current. So let us do an example. I hope we have time to finish this. Okay.
Hello.
Any question? Yeah, please
Yes.
go on.
Should that be short circuit or open circuit?
Sorry?
Should that be short circuit or open circuit?
Short circuit for current.
So if it's voltage, you're talking about open circuit.
Open circuit, yes.
That's OC, VOC. That is, you're talking about voltage. If you're talking about current, it's short circuit. ISC, that is this very one. This is short circuit. This short circuit current, 9.60. This is open circuit voltage, 45 volts.
It's noted. It's noted.
At short circuit, current is 0. I
Sorry?
mean, voltage is 0. At short
Exactly.
circuit, voltage is 0.
Exactly.
There's
maximum power point and maximum power point current and maximum power point voltage is the voltage at maximum power point and the current at maximum power point. I explained all of this in our first class on solar system. Please, you can refer to that video. So let us look at this example. Now, to understand this step, that's what we've talked about, in more mathematical way, let's take an example of a power plant. Let's take an example of a power plant of 2 megawatts. It's a power plant of 2 megawatts, in which a large number of PV modules are connected in series. Okay, of course, you need to connect them in series to increase the voltage. Of course, 2 megawatts, it means that you're feeding into a high voltage network. So you need to connect in series to increase the voltage to a high voltage network. So the 2 megawatt inverter can take input voltage of 600 volts. Now, this is the inverter specification, 600 to 900 volts. So if you have an input voltage of between 600 and 900, then it is fine. The inverter is fine, but you don't go beyond 900 or you don't go below 600. The inverter might blow up or not work very well. Now, the question is, determine the number of modules to be connected in series to obtain a maximum power point. That is MPP, maximum power point voltage of 800. Now, we want the voltage at maximum power point to be 800. Also determine the power delivered by this PV array with the following parameters. So this parameter of the single PV module as follows. Open circuit voltage is 35 volts. Voltage at maximum power point is 29. Short circuit current is 7.2. Current at maximum power point is 6.4. So this is the kind of characteristic you see on your PV modules, right? So what do we want to do? We want to know the number of PV that we can arrange in series to get a voltage of 800 using these characteristics of a PV module. I hope the question is clear. Let us. Okay, so now look at this PV. Can we determine the power of individual module? MPP, the MPP power of an individual module. I just want to test our understanding. Please, can any of you calculate this and tell me what is the, that's one module of this PV having this, what is the power?
The power should be 29 times 6.4.
Okay, is anybody in disagreement with this? Okay, so he's correct. The power is 29 times 6.4 of individual module. That is the power. So the power of one module here is 185.6. Right? So now the number of module to be connected in series will now be now the maximum voltage of the array. We know the voltage of the individual modules, correct, which is 29 volts. And we want to know how many we're going to connect in series to arrive at 800. Is that correct? So we divide 800, which is the maximum voltage of the array, by the individual voltage of the module. So we divide 800 by 29. 800 by 29. So this is the number of PV modules that we can connect in series to get 800. But of course, you know, you cannot have 27.58. You just have to make it a higher integer of 28. But when you make it a higher integer of 28, you also change the voltage. So you're going to get a voltage that's going to be more than 800. So let us now know what the new voltage would be. So take a higher integer of value of
the last slide, please. Sorry.
Okay. You mean this? Hello, is this okay? I can't hear you. You're not responding. Okay. So when we increase now when we do this division, we're going to get 20, just like when we did the battery. Remember, when we did the battery, we have to increase it to a higher integer and depending on the number of pairs that we need. Now for PV modules, we wanted to get 800 volts, but you cannot get a fraction of a PV module. So you have to increase it to the highest integer, which is now 28. But when you do that, you also increase the voltage that you're required to get. But of course, it's a slight margin. It's just slight margin. So we need to calculate what will be the new voltage. So the new voltage will now be 29, which is the individual voltage of the PV module, times 28, which is the number of PV module we want to put in series. When we do this multiplication, you have 812 volts. So which is still close, it's still okay, it's still okay, it's still within the tolerance limit of the inverter. So it's fine. So this voltage can go into your inverter. So this is the voltage or the number of PV that will require to meet this voltage. So total power of the PV array, that is the total power of the PV. That we also asked to calculate what is the total power that can come out from this PV array, right? Now, the total power of this PV array will now be the number of module, the number of PV module times the MPP maximum power point of individual module, which is output power of individual module, which we have first of all established to be 185, right? So okay, so when you multiply that, the number of which 28 times 185, you have the output power of that array is 5,196.8 watts. That is output power of that array. Thus, we need 28 PV modules of 185.6 watts to be connected in series, having a total power output of 5,196.8 watts to obtain the desired maximum voltage, maximum PV array voltage of 800 volts. So this is just example. I think there's another example that we can look at. So calculate the number of PV modules required in parallel to obtain a maximum power point current. Now we are talking about current this time of 40 amps. Now the system voltage is 14 volts. The parameter of the single PV module is given below. So this is the parameter of a single PV module. Open circuit voltage, voltage at maximum power point, short circuit current at maximum power. So what will be the power of this PV module?
What?
84 what?
That's
14 times 6.
Times 16 amps. Times 6 amps.
14 times 6, that will give you the power output of the PV module. But let's look at the solution. So the number of PV modules required to be connected in parallel. Okay, so the maximum current of the array that we need, which is 40, in the question they told us that we want to get a maximum current of 40 divided by the current of individual module, which is 6 amps. Now this current of the module is the current at maximum power point. Not current at short circuit, current at maximum power point. So when we do that, we will now have a number of PV, which is going to be 6.66. But of course, you cannot have a fraction. You upgrade it to the higher integer of 7. So that's an exercise that we've done. So this is an assignment exercise you can do and then share on a WhatsApp platform if you want to. So this is saying calculate the size of the PV panel. You're calculating the size of the PV panel, you're calculating the size of the inverter, you're calculating the size of battery bank, charge controller of the following requirement. Now the load in our own case is 410, which is what we still have. But in this case, the energy requirement from the solar PV is 3,400, the same thing that we have in our own case. And then in this case, it's actually to consider 1 day of autonomy for battery storage. So this is the same thing that we've done in the worked example that we did. But in this case, in the worked example, we consider 3 days of autonomy. But in this case, we're asking you to consider just 1 day of autonomy and do the same calculation. This is just for your own practical exercise. If you want, you can put your answer on WhatsApp group. Otherwise, I mean,
no, I thought in the worked example, we did 2 days autonomy. Not 3 days.
Sorry, 2 days of autonomy. Yeah, sorry, 2 days of autonomy. Yeah. So, but in this case, asking for 1 day of autonomy, please. Yeah, thank you for that correction. Yes.
Okay.
Yeah. So I think that's all for today. We're able to manage the time very well. Okay, so we have about 10, 14 minutes. Do you have any question regarding what we presented so far today? Maybe we can just use that to, ask questions. If for any
Chima,
of you are, yes, please.
Chima, I have a question now. I need more clarification on this autonomy, how to detect the right autonomy, to assume the right autonomy for an installation. Need a guide. You said something about the cycle, and each of the battery has a cycle. So shed more light on how you can use that cycle to deduce or assume an autonomy for a particular installation of choice.
So these are two different things. These are two different unrelated issues. Days of autonomy is unrelated to the number of cycles the battery can go. Yeah, the number of a cycle. Now, when you go and buy a product in the market, sometimes you see an expiry date. This is the expiry date of the item. Now, when you buy a battery, you need to know how long you can use this battery before you might need to change it. And let me also state that when you see 6,000 number of cycle, it does not mean that after that 6,000 number of cycle, the battery is useless. No, it's only telling that after that 6,000 number of cycle, the capacity of the battery will reduce. So if the battery is able
the battery is derated.
Is
that
derated,
what is understood. I'm talking about the autonomy now.
Okay. So the autonomy is discretionary on your client, on your client. If the client wants, look, the client can tell you, look, I want this system to run continuously for 3 days, uninterrupted, even if there is no sun, then you should know that you have to include 2 days of autonomy in your design. But like I said, if you have to increase your battery capacity, it comes with a heavy cost. So you need to do the economics. A lot of times you go to your client, they will just say, oh, I want to power AC. They will mention so many that they want to power without minding the cost. It is you that will now come and tell them, look, this is the cost implication. You can even ask what is your budget? I've got many clients which I think at this point I need to stop the recording because we've completed our business for today. There's something I want to touch on. Please let me go back and touch on something which I think is very, very important. I want to talk about shading. I don't know if I talked about that in our previous class when I talked about half-cut solar system. I think I mentioned it, but let me just repeat that because it's very, very important. Shading is very, very important in solar systems. Okay, when you have a solar installations, so assuming that you have this solar installation connected in series, okay, and then you have maybe dead leaves fall on this cell, just one of this cell, okay. If these solar panels are such that they don't have diodes in between them, and just one of this cell that is being covered by dead leaves, the output from this cell will be reduced. So if this output from this cell, for example, if the contribution of this cell is about maybe, for example, let me say maybe 20. Let me say 20 output from this cell, maybe say it's 20 watts, okay? What's going to happen to this entire series connection is that they are all going to be reduced to 20 watts. Meanwhile, this ideally is should come out at 180 watts, correct? That's the three of them combined should come out at 180 watts. But if this cell, I think 20 watts is even too much. Maybe this cell is contributing 5 watts or 2 watts, right? If dead leaves covers this cell, it's going to reduce the entire output of this to 5 watts. So to avoid some of this thing, the manufacturer have now decided to put a diode in between this panel. So if you have how many columns here? 1, 2, 3, 4, 5, 6. So these 2 columns will have a diode between them. These 2 columns will have a diode between them, and this last column will have a diode between them. So if there's a shading in this column, it will only affect this. If there's a shading on this cell, it's going to only affect these 2 columns. These other columns and these other panels will work as normal. Okay, so I think I just need to re-emphasize this shading effect on solar panels so that when you're designing, please pay attention to shading because creates a lot of problems in the design systems. When you do your solar installations and maybe some part of the panels are being covered by shading, maybe by near buildings or by whatever it is, and you don't take that into consideration, it can greatly affect the entire output of your solar panel. Again, when you go out in the market to sort for solar panel, look for those that can at least have some high tolerance for this shading. Look for those that have those diodes, those connecting diodes. And also, that's also the reason, part of the reason why you've seen solar panels that have half-cut solar panels is also to reduce some of those shading losses, to increase solar panel efficiency, as well as losses. The losses of the current when they move through these solar cells. I think what I'm saying now has already been explained in our initial video, but I'm just, for emphasis, I'm just trying to repeat that because I thought it's important that we have that common understanding. I think that being said,
yeah, I have a question.
Okay.
I also have a question.
So my question is on this cycle you mentioned. I quite understand it, but does